Welcome you all to the video on error probability performance of binary orthogonal signals. So in this particular video, we are going to deduce an expression for the bit error probability for the binary orthogonal signals. So orthogonal signals are the ones where the carriers of the symbols are uh, not correlated to each other. That means the dot product of the two carriers, if suppose if F1 and F2 are the two carriers, then the dot product of the two carriers will always yield a 0. So F1 into F2 will always be equal to 0. That means we can assume the angle between the two carriers, theta 1 2, will always be equal to 90 degree. That means they are orthogonal to each other. So if such carriers are used during for the as a carrier for the transmission of binary symbols, then we are going to obtain a um, modulation technique called as binary FSK, because in the frequency modulation in the frequency shift keying itself, we are going to use the frequencies F1 and F2 for the transmission of the symbols. So in an FSK, the symbols are represented as S1, which is S1 representing either binary 1 or a binary 0, is always represented as under the root 2 EB by T into cos omega 1t, and the symbol S2 is given as under the root 2 times EB by T into cos omega 2t. So these are the two symbol representation for the binary FSK. If we have to represent these symbols over a signal space representation, then we can write the basis functions. Since it involves two basis functions, we are going to represent it with two-dimensional plane, where xi1 and xi2 happens to be the orthogonal axis of this signal space, and xi1 is given by under the root 2 by t into cos omega 1t, and xi2 is given by under the root 2 by t into cos omega 2t. So how to represent the symbols S1 and S2 is we have to move from the origin with an amplitude equal to under the root EB and mark along xi1 to obtain the symbol S1, and uh, move along in the direction of xi2 for an amplitude equal to under the root EB and to obtain the symbol S2. So these are the locations of the symbol S1 and S2 whenever we are transmitting a binary FSK signal. So this can also be written in the form of matrices, which look something like this. Symbol S1 can be determined as the signal point with an amplitude under the root EB along only xi1, and the xi2 component is equal to 0. S2 can be similarly written as the signal point with 0 as the component along xi1 and under the root EB as the component along the basis function xi2. So these are the things that we have known for the binary FSK. Now, in order to determine the performance or the probability error, probability of bit error during the transmission over an AWGN channel, let us consider that the scenario where S2 symbol is transmitted. S2 symbol is transmitted. So this is the condition that we are considering to begin with. So if an S2 is transmitted, then the received signal R will consist of S2 plus the noise along the frequency omega 2 or frequency omega 2, frequency F2. So therefore the noise which is affecting the symbol which is transmitted with the frequency omega 2 will only be affected by the noise with the frequency omega 2. Therefore that type of noise we call it as N2. Similarly, if S1 was transmitted, Then the noise that is impacting the symbol for during the transmission is the another set of noise which is present at the frequency omega 1, and that we can name it as n1. So basically, if the symbols are orthogonal to each other, even the noise associated with the symbols are also orthogonal to each other. This is because of the reason that, assume that I have obtained the received vector r. If I'm trying to project the component of r along the xy1, I obtain a component of r called as r1 dash, assume. So this r1 dash will consist of both symbol as well as the noise. So therefore, not only the symbols are orthogonal to each other, noise affecting the symbols affecting the symbols are also orthogonal to each other. So, keeping this in mind, let us see what will happen if the symbols are transmitted over a channel without, and they are not corrupted during the transmission. If at all the symbols are not corrupted, then in the signal space, I obtain the absolute symbols with their amplitude as root EB. So, in that case, the position of the symbol S1 would be along the basis function xi1 with an amplitude r1. I'll name that as r1, which is equal to under the root EB. Similarly, the uncorrupted symbol received, S2 received, can be written as r2 with an amplitude root EB. Now, what if I receive, so the base, let us first try to write the decision boundary to this. Whenever we have two symbols, s1 and s2, there has to be a boundary which has been fixed to determine on the receiver what is the which is the symbol that was actually transmitted. So to determine that, the normal method to determine or fix the decision boundary is to draw a line between the two symbols, s1 and s2, and exactly cut the line between these two in the midway, and pass that perpendicular line through the origin to obtain the decision boundary. So this is what we call it as the decision boundary between the symbols s1 and s2. What if the received vector lies along this region, then we decide in the favor of symbol r1. If the received vector lies in this anywhere in this region, then we decide in the favor of symbol r2. So this is the scenario that we will be making use of. So let us consider, as of now, the S2 symbol was transmitted and we have obtained the received vector, because we are trying to obtain the error probability. So therefore we are creating a error scenario where uh, we know that S2 was transmitted, but the received vector is such that it is lying in this region. It is lying in the region corresponding to the symbol r1 or the symbol s1. So how do we mathematically say that this received vector is going to be ended up in an error? This we will see. So what we do, as soon as we obtain a received vector r, we are going to project it to the individual basis function axis, and this projected value, let us name it as r1 dash, and this one is r2 dash. So having known this, so if I have sent an symbol r, symbol s2, I should have received r2, but I have received r2 dash. Therefore the noise that is affecting this symbol is called as n2, which has effectively reduced the amplitude of the r2 to this particular value. So r2 dash can be written as r2 minus n2. Similarly, for the transmission of the symbol s2, So S2 was transmitted is a scenario that we have considered. For the transmission of the symbol S2, we have seen over here, for the S2 there is no component along the basis function 1, but still there is some projection that is happening along the x-axis. So this projection is only due to the noise that is present along the frequency omega 1. So this r1 dash can therefore be written as is only due to the noise, and we can be calling this as n1. So when do we say that the error has occurred? The condition or the correlation expression to say that the error has occurred, we are the correlator matrix, that is r comma s1 will be greater than the correlator matrix r comma s2. This is when we call that the error has occurred. So this is the probability that the error has occurred. Given that s2 was transmitted, we say that if the correlator is mainly the correlator is being showing the component with s1 with a larger value when compared with the correlator with s2. So this is the scenario where the error has occurred. So now let us see what is this condition is. So keep this in mind. So or else we can also say that if the projection of r1 along the xi1 is, if it is larger than the projection of the received along xi2, then that is also, this is the error condition. So ideally r1 dash should have been 0 and r2 dash should have been equal to r2 for a proper transmission. Now we have got to know that it has been corrupted and they have their own individual noises corresponding to the basis function. So considering this error condition, we will proceed further. R1 dash is equal to n1 will be greater than r2 minus n2. So this is the scenario. So rearranging the terms, I get n1 plus n2 is greater than r2. So all the noise terms will be clubbed together. That is n1 plus n2. If the magnitude of the noises along when they are put together, that is n1 plus n2, if it is greater than root eb, then we call this scenario as the error condition. That is, magnitude of the noise along both the frequencies, if it is larger than that of the signal energy, then we decide that the error has occurred. So since n1 and n2 are uncorrelated, that means n1 and n2 are orthogonal. Uncorrelated means the other representation or the way of expressing is uncorrelated means they are orthogonal to each other. Their power spectral density will be such that the total power spectral density sigma naught square will be equal to sigma 1 square plus sigma 2 square. Remember, the noise that is affecting the signals along the basis functions I1 and I2 both are of type AWGN with the probability density function or probability with the power spectral density equal to n naught by 2. So keeping this in mind, psi1 square will be equal to n naught by 2, which is the PSD power spectral density of noise n1, and similarly sigma 2 square will also be equal to n naught by 2, that is, which is the power spectral density of n2. So only therefore the total noise power spectral density will be equal to n naught by 2 plus n naught by 2, which is equal to n naught. So this will, let us call this noise as n naught of t, which is the summed up version of n1 and n2, and the PSD of it is power spectral density of n naught is capital N naught. We know that, let us write now the PDF function of n naught. Now the error, for writing up the error condition, we are now come up with an error expression with n1 plus n2. If it is greater than root EB, then this is the error condition. So therefore we are going to express or obtain the error probability expression based on the probability density function of the noise n naught. So fx, or we can also call this as the probability density function. Okay, let us write this as fx of n naught of t. The probability density function is given by under the root 1 over under the root 2 pi into sigma naught square into e raised to minus n naught of t whole square divided by 2 sigma square. This is because n naught is a zero mean Gaussian noise. Therefore, the mu term is not there. So knowing this much and also substituting sigma naught square is equal to n naught, we obtain fx of n naught of t is equal to 1 over under the root 2 pi into n naught into exponential minus n naught of t whole square over 2 times n naught. So what do we understand by this is, let us draw the probability density function curve for the given noise, that is n naught. So it's a bell shaped curve, as we know. This is the, on the x axis I have all possible noises of possible amplitudes of the noise n naught, and this is the fx, that is probability of occurrence of the noise amplitude n naught. So this is the zero mean. So what does this state is, the error condition, depending on the error condition, we can say that the added sum, that is n naught is equal to n1 plus n2. If n naught can be mapped over here, if the value of this n naught, if it exceeds a certain value of root EB, assume that this is n naught, I have some n naught, this is the reference value under the root EB. If this n naught is greater than under the root EB, then we call that particular case as the error condition. So therefore, marking this root EB, if the n naught is greater than this value, then the error region will be given by this portion, because all the values of n naught beyond this root EB, it is said to be an erroneous region. So this is what we call it as error region. So what we need to do in order to determine the probability of error caused in this scenario, we have to integrate the probability density function fx of n naught from the value under the root EB till plus infinity. So that is what we are going to do now. So the probability of error PE can be written as 1 over under the root 2 pi into n naught integration from n naught value or root EB value till infinity. What do we have to integrate? It is the the probability density function of the noise, that is e to the power minus n naught of t whole square divided by 2 times n naught into d n naught of t. Why we are using d n naught of t is because we have taken the random variable as n naught, which is the added sum of n1 and n2. Now substituting in place of the small n naught, the value from which we correspond it to the error region, n naught should be greater than under the root EB. So that starting point is root EB, therefore we are writing it like this. The lower limit of this integration is under the root EB and the upper limit is till plus infinity. So e to the power n naught of t whole square divided by 2 n naught into d of n naught of t. We will do the substitution now. So put y is equal to y square is equal to n naught of t whole square divided by 2 n naught. So therefore y will be equal to n naught of t divided by under the root 2 n naught. So dy will be equal to 1 over under the root 2 n naught into d n naught of t. Substituting all these into the above integrand, we are going to obtain 1 over under the root 2 pi into n naught. Let us see what will happen to the limits also. When n naught of t is equal to root eb, y is equal to under the root eb by 2 n naught. Under the root eb by 2 n naught. When n naught is equal to infinity, y is also equal to infinity. So we can substitute the lower limits and upper limits. So this is root eb by 2 n naught till infinity e to the power minus y square into under the root 2 times n naught into dy. So this I am substituting it over here. So having done that, let us see what will happen. This 2 n naught under the root 2 n naught and the under the root 2 n naught here will get cancelled. So I'll be left with under the root 1 over under the root pi with the integration limits eb by 2 n naught till plus infinity e to the power minus y square into dy. So this is a standard expression. We can bring this into a standard expression by multiplying and dividing it by 2, because this does not change anything. The standard form is that the 2 over under the root pi integration from u to infinity to the power minus y square into dy is nothing but the complementary error function called as ERFC of u. So using this we are going to express this above equation. So what we do, we are going to combine to bring this into a standard form. We have multiplied and divided by 2. So we are trying to put these things together. So we have 1 over 2 left over as is. So p is equal to 1 over 2 we are left out as is. The grouped part will be written as ERFC of the lower the value on the lower limit, which is equal to under the root EB by 2 n naught. So this is the expression for the probability of bit error for the binary orthogonal signal or binary FSK signal. This can also be written in terms of Q function. As we know, PE is equal to, ERFC and Q are related as ERFCN and Q are related as ERFC of U is equal to 2 times Q of root 2 into U. So using this expression we are going to write the in terms of Q functions, this is half into 2 times Q of root 2 into under the root EB by 2 n naught. So writing this 2 will get cancelled, this root 2 and this root 2 will get cancelled. So we are left with the Q function of under the root EB by n naught. So this is the expression for the binary probability of error function for a binary probability of bit error of binary orthogonal signals. So this expression can also be written in terms of the distance between the two symbols. Like if we are going to express this, so the distance between the two symbols for the binary FSK is this is root EB and this is also root EB. So the distance between them is formed by the hypotenuse of the right angle triangle on including the origin. So therefore this can be given as, let me name this value as d12. So d12 square is equal to root EB whole square plus root EB whole square, because the sides of the triangle are root EB and root EB. So d12 square is equal to EB plus EB, which is d12 is equal to under the root 2 EB. So using this expression, I will write this as like this. So the numerator part can be written as d12 over under the root 2 times n naught. So this is the expression in terms of the distance between the two symbols for an orthogonal binary orthogonal signals. So I thank you all for watching this video. In the next video we will see how to obtain the error probability expression for a QAM signal. Thank you.